Welcome to EDU World Space.
Let's see if we can figure out the equilibrium partial pressure of carbon dioxide in a particular chemical reaction. So let's take a look at the decomposition of barium carbonate. Now, if you notice in this chemical reaction, the only gas or aqueous substance is carbon dioxide. Barium oxide and barium carbonate are solids. So if we want to know the equilibrium pressure of CO2, we're going to have to deal with equilibrium. And if we were to come up with the value or the expression for the equilibrium constant here, remember solids don't go into the expression when we use the law of mass action. So it actually turns out here that the pressure of carbon dioxide at equilibrium is also the value of the equilibrium constant. Well, how are we going to get the value of the equilibrium constant? Well, we're going to have to use enthalpy and entropy values in order to come up with the Gibbs free energy. And so we can, if we kind of work backwards here a little bit, if we know the Gibbs free energy, we can relate that to the equilibrium constant. We know that we can do that because K can be equal to E to the negative delta G naught over RT. However, when we have our delta G, we have to be able to account for temperatures. So we're going to have to calculate the delta H and the delta S as well. We especially have to do that if we're not at standard conditions. And so if we look at anything other than 298 Kelvin, we can't just use delta G values from tables of data because they're not going to be at 298 Kelvin. So the way that we're going to have to deal with that is to calculate delta G with delta H minus T delta S. So we can only have the naught when we're at 298. Anything other than 298 Kelvin, we need other values. So we're going to have to do a lot of calculation here to figure out what the equilibrium constant is, because we're also going to need then to figure out the delta H and delta S. And we're going to need to use the fact that the delta H of reaction is equal to the heat of formation times the number of moles of the products minus that of the reactants. Same thing for our delta S. So we're going to go look for, in our table of values, for the H's of formation for each of our substances, the entropies of formation for each of our substances, calculate the delta H and delta S of reaction. We're going to plug that in to delta G equals delta H minus T delta S to find the delta G. And then we're going to use that delta G and whatever temperature we've got in the equation for the equilibrium constant to find the value of K. And we created our law of mass action way up here at the beginning. And we know for this particular reaction, the equilibrium constant and the pressure of carbon dioxide are the same. All right, so let's go ahead and get those values and work through this problem. So let's figure out the delta H first. All right, so the delta H for this particular reaction, we can go find the values of the barium oxide and the carbon dioxide because we have to deal with the product side first. And we have 1 mole of each. So we have negative 553 0.5, and we have negative 393.5. We're adding them together because the reaction says take the sum. The equation says to do that. And we're going to subtract that of the reactants, which is negative 1216.3, to get the value 269.3 kilojoules for the delta H. Now we'll go and do the delta S. We do it the same way. And so we have 70.42 and 213.6 is our entropy of formation values for the product side. And we're going to subtract 112.1 for the entropy of formation of the reactant side. And that's going to give us a value of 171.9 joules per Kelvin. But we're going to wind up putting it in to try to find delta G, which has to be in kilojoules. So we're going to divide this value by 1,000 to get 0.1719 kilojoules per Kelvin. And now we can take these values and plug them in to find the delta G. Now first, we're going to figure out what the delta G is at standard conditions. And if we were only looking at standard conditions, we could have directly gone to do a delta G, sum of the products minus sum of the reactants, but we're also going to look at it at a temperature other than 298. So we might as well go through this process now because we can use these values in both scenarios. And so now if we want to know what delta G is, we're going to do delta H minus T delta S. So we're going to have 269.3 kilojoules minus, and our temperature to start out with is 298 Kelvin. And we have our delta S as 0.1719 kilojoules per Kelvin. So we're going to wind up with our delta G naught as 218.1 kilojoules. Now that we have that number of kilojoules for delta G, now we're going to go and use that delta G to find the value of K. So K is going to be, as it was written up above, E to the negative delta G naught over RT. And so let's go ahead and plug those numbers in. And we have our negative 218.1 in the numerator. In the denominator, we're going to have R and T. R is 8.314 times 10 to the third power, because we're dealing in kilojoules instead of in joules. And we're going to multiply that by our T, 298 Kelvin. Just to clarify, that should be to the negative third power. And we wind up with our equilibrium constant as 6.0 times 10 to the minus 39. And remember what we set up above, that was also equal, in this case, to the pressure of carbon dioxide. So the pressure of carbon dioxide in this case is 6.0 times 10 to the minus 39 atmospheres. Now this is what happens at 298 Kelvin, but what if we do this at another temperature? What if we do this instead at 1100 Kelvin? Well, we don't have to go back and calculate the delta H and the delta S again. But what we can do is plug those numbers in for delta G changing our 298 into 1100. So why don't we go ahead and do that? So we can have our delta G is still equal to delta H minus T delta S. And we know our values from before, 269.3 kilojoules minus 1100 Kelvin times 0.1719 kilojoules per Kelvin, which is going to give us a value of 80.19 kilojoules. And now we can plug that in to our equilibrium, and we can say that K is going to be equal to E to the negative 80.19 over 8.314 times 10 to the minus 3 times 1100 Kelvin. And we're going to wind up with a value this time of 1.6 times 10 to the negative 4. And remember, in that case here in atmospheres, that's also going to be our pressure of CO2.